So let me start from what we were doing last time. There was a problem which we left unfinished. So let me just first complete that. So the problem was related to when you have a statistic of the variance itself. You're picking a sample, and the sample variance is a random variable now, because every time you pick a sample, you pick a different set of data points, and when you compute its variance, you get a different number. So the problem was that there is a company and they are making some electrical components with a certain resistance, which has to have a very specific value for safety reason, let's say. That means you are putting a control on what is the standard deviation on this resistance. So suppose the standard deviation is controlled to be, control means it is encoded in your process, that it shouldn't be, it's expected to be, or controlled to be, or expected to be equal to 3.6. And you are sending out shipments every day of these components, and you want to make sure that you're not only concerned about the mean value of the resistance, you are even concerned about that what is the distribution, how far away they move around the mean in your production process. Obviously, you cannot make sure that every resistance has exactly same value. There are some differences in the components, and suppose in your process you're expecting a standard deviation of 3.6, and it's known that the distribution of resistance values is normal, because in this case you can say something about the variance, distribution of the variance in a sample. It is normal. So you pick a sample of size n. So every day when you send out shipments, you check on them by taking out 6 random components and compute their sample variance. Now we know that the way you compute the sample variance is you compute the sample mean, and then you take all these values to make the difference, sum over all elements in the sample, and divide by n minus 1. You just slightly change the formula where n is the size of the sample. So this is what you are computing. And
Sir, I have a question.
yeah, say again.
Sir, I have a question.
Yeah.
So you said that distribution of resistance values is normal.
Yeah.
What do you mean by this statement?
Well, it's a normal distribution. Were you in classes in last few lectures? So you have a mean, which is not told to us in this problem. So let's say this is the mean value of the resistance. but not all components are expected to have exactly this value. And they are distributed in a normal, using a normal
Okay, okay.
distribution.
Yes, yes, sir. I get it. I get it. Thank you, sir.
Mhm. So this is the number you compute, and this is a random variable, but we know this, that this is equal to actually the expectation value of this random variable is equal to the variance of the population. So this is what we expect, but every time we pick S square, we pick get a different number. Now you want to say what would be the sample variance cutoff value so that the probability of it exceeding that value is less than a certain tolerance. So suppose you put in, you pick a sample and get a particular sigma, let's call it sigma star. You know that these sigmas will be distributed, so sorry, S square, get a certain S square. You know that they're distributed around sigma square. The mean value is sigma square, but you also know that these S squares, they are all bigger than zero. These are positive numbers. And you know that what is their distribution? And the distribution would be the chi-square distribution. Distribution. And this is defined through this variable chi-squared with an index n minus 1. So for the sample of size n, the variance will be according to a chi-squared variable, which is defined this way. So this would be the relation of a chi-squared, which is a standard distribution, just like we have a standard normal whose properties we can look up in tables, which we know we can compute easily. So similarly, this chi-square is a standard distribution, looks, depending on what value of n you are using, it takes certain kinds of shapes. We don't need to compute. We have tables and we have calculators to do it for us. But this is the relation between your variable, which is your random variable right now, S square, and this chi-square distribution. So you want to make sure that your shipment, when it goes out, so all the components in shipment are like a population. And there you are expecting sigma to be 3.6. If sigma is 3.6, correspondingly there is a distribution on S square. S square is this variable, sigma square over n minus 1. So this S square picks values according to this distribution. And you want to make sure you have a tolerance level that there's a 90% chance, well, let's say a 95% chance that you can get a value of S square less than a critical value. So this S square takes certain values, and over here there will be a critical value of S square that having S square more than this, so you have certain distribution. This area is only 0.05 because the total area is 1. It's a probability distribution. So having a probability that you have S square more than this number is only a 5% chance. So if this number shows up in your sample, you can be a little worried that maybe it's really a 5% chance that this happened, or if this unlikely event happened, then I should probably go check. Maybe something is wrong in the population. Maybe sigma square itself, or sigma in population itself has changed. So it depends on your process, how you, maybe you can put a 10% chance that whenever there's a 10% chance that I am exceeding, that I'm getting a value which only had a 10% chance to come up, then maybe something is wrong in my population, what I was assuming for the population. And you can go and check your shipment throughout. So how would you compute this chance? Let me see what's the question. S square is just the variance of the sample. It's written over here. Variance of the sample. So you are trying to guess, you're trying to see the variance. Remember, what is variance? Variance is standard deviation square. That's the formula. In a sample, so you are trying to get an idea of the variance in the population, the standard deviation of the population, using the variance of the sample. But you know that the variance of the sample, it will have a mean which will match with the variance of the population, but it will be a random number. You will not hit it every time, and you are counting the probability that if you move away from this number, how much is the probability. So you have this chi-square variable, and you have this relation. S square over sigma square. So in our case, it would be a chi5 variable. Square is just a symbol. It's always written as a square. You don't need to ever take a square root of this thing. It's just its name. N minus 1 is 5 for us. S square. Sigma square is 3.6 square. So that's 12.96. Now I want this, that the probability of the corresponding chi-square variable, 5, 1, is only 5 to exceed a value A. So corresponding to S square, there is a chi5 square variable with certain probability distribution. And there will be a critical value, A over here, so that this area is 0.05. So this I want to compute. So again, for this time, let me do it on the online calculator, and in a minute I'll show you how to do these things on SPSS. Let me change the my
Sir,
yeah
sir, 3.6 was population variance.
population standard deviation. So you have to
Oh.
scale it to get the population variance. Uh, Let me change the screen. Okay. So I have like this chi-square calculator over here from the same website, stattrack.com. It has all kinds of online calculators for various probability distributions. So I put in, uh, it asks for the degree of freedom, which is this this index, lower index on this thing. So it is 5 for us. And I want to compute the chi-square critical value, where the probability, because it tells me the probability of chi-square being less than 11 point, less than, well, I should probably do a new window. Yeah. So this is 5, and I want to compute a chi-squared critical value. Over here, it's giving me an option of being chi-square being less than a certain critical value. So it is computing the probability of chi-square being less than this. But that I know being less than A is equal to same as probability of total probability is 1 minus probability of chi-square being greater than A. So I can compute the same critical value by saying that the probability of chi-square being less than this critical value is 0.95, because 0.95 plus 0.05 would be 1. So I just put in 0.95. So it automatically fills in for me this option, which is that the chi-square is greater than this value. That probability is only 0.05, as it should be. And then I just calculate, it gives me the number 11.1. Let's look at it from the table. If I can go there. If I can quickly, let me see. I think it was table number 10. This is F distribution. Yeah, this is the chi-square distribution. Now, this is the number 5. And this table, because it cannot do a lot of computation, so they have given these two tables. That chi-square being greater than a value, these are called the upper critical values. So it tells you if chi-square, if the probability is 0.1, what is the upper critical value? That the probability of chi-square being greater than this particular value. So for example, if I pick nu is equal to 5, And now for me, I wanted to know that the chi-square is greater than a particular number, a particular critical value, and that probability should be only 5%. So I look in this table and it gives me 11.07, slightly more accurate than what the calculator gave me. So it gives me 11.07. On the other hand, it also gives you the lower critical values as well, that the chi-square is greater than a certain number and that the probability is 90% of that being chi-square being greater than that. So it gives you these lower critical values as well in the next table. So it covers somewhat this area up to here and then this area up to on the starting tail and the ending tail. So I can look up from here, it gives me 11.07. The calculator gave me 11.1, which are almost same. So this gives me the chi variable to be, let's pick up this value from the table. And then I use this expression to compute S square. $28.69. So S is 5.38. S square. S is 5.38. That means I compute the sample variance, and if the sample variance exceeds this value, so sample variance is going to be a positive number, and if it exceeds this value, I know that this thing happening had only a 5% chance. So I'm a little worried and I go check my shipment. Now let us come back to the study of what we have been doing so far, just developing the main ideas, basic ideas of how to estimate a population characteristic from a sample. So let's do it let's collect some examples that what kind of situations we generally encounter when we are doing this thing. So what kind of population characteristics we are usually interested in, and what kind of things we can do on the samples to get to try to estimate those population characteristic one by one. So we want to study population. Well, I should say we want to estimate some population characteristic. So it could be, for example, population mean, population variance, population proportion for some variable, and you want to estimate it using a sample. So let me just stop for 2 minutes. There is azan here, so it's way too loud. So let me just stop for 2 minutes. Don't go away. I'll be back. So you are interested in some population characteristic and you want to estimate it. You have no idea what it is. You want to estimate it by picking a sample. So using a sample, you have an estimator. So that means some variable that you use to estimate population characteristic. So for example, if you are interested in population mean, you can probably take the estimator to be the sample mean, because you believe that is going to give you some good idea about the population mean. Similarly, for population variance, you had the sample variance. Well, usually it's pretty straightforward. You kind of do the same thing which you are doing in the population, you do it on the sample, and that gives you an estimator for the population in the sample. However, this estimator is always, because you're picking sample, it is always a random variable. So you do not expect to hit, when you estimate, you do not expect to get the same answer as the population characteristic. However, it would be usually considered a good estimator. It's called an unbiased estimator. Because it will be a random number, it will have its own probability distribution. If you compute, so suppose if this is, if this estimator is denoted by theta hat, and let's say the population characteristic is theta. If the mean, the average value of this estimator, according to its probability distribution, is same as the population characteristic, whatever value of this characteristic of this thing in the population, then you say it is unbiased. So as we know that the population mean is unbiased, and sorry, the sample mean is an unbiased, estimator of population mean. Similarly, the sample variance is an unbiased estimator of the population variance. And when you will estimate using an estimator, an unbiased estimator, you get a particular value. A particular value of the estimator variable is called the estimate of the population characteristic. Now, this estimate would be generally according to its whatever probability distribution is. If this is it's unbiased, this is the population characteristic, it will be spread around it. A particular value will be spread around the mean value of this estimator. So in a particular hit, you will not get exactly this, you will get some other value. And depending on how tight is this distribution. In other words, smaller the variance of the estimator, the better chance you have that you will guess the you will land close to the population character, the true population characteristic which you want to estimate. So the estimator, more chance you have of guessing of estimating the population characteristic accurately. So smaller the variance, you say that it's more efficient is your estimator. Then there are the most efficient estimators. We know that sample mean is the most efficient estimator of population mean if the sample if the population is normally distributed. So now let's go one by one into various problems we can encounter when we are trying to estimate some characteristic of the population. So the first case is that your population is known to be normal, whose standard deviation is known, and you want to estimate its mean. So now if you want to do that, you will pick a sample, and you compute. So in this case, your estimator would be sample mean, which is denoted by X bar. And you know that there is some distribution. Let's say this is the population, and this is mu. This is the population mean mu. You know that this sample mean, this itself will be distributed according to central value theorem around this population mean according to a normal distribution. And this would be same as the mean value of X bar. If I plot X bar, it will be itself will be like a normal distribution. But on the other hand, the population, if I draw on the same graph, the values of this variable in the population, that will also be some kind of a normal, typically with a, not typically, always with a greater variance. It is given to me that it's also normally distributed. Now, when I pick a particular value, I can put I know that it will be a particular value of X bar will hit somewhere around here. I will not always hit at mu. And being away from mu and being within a certain range of mu will have a certain probability. So for example, I can ask, what is the interval of sample means, mean values, so that I have a certain, let's say, beta probability. That means beta times 100% chance that the sample mean will be from this interval. Well, it will be some interval, you can compute it. AB, and since in this case, the this probability distribution is symmetric, and I'm computing that so this, therefore this B will be, they will be actually same. It would be between minus A and A. Let me first write AB.
Sir, your last point, please.
Well, let me first write this way. AB. But this B, A would be minus B because it's symmetrically distributed. So whatever the probabilities you have on around on whatever area you have here is same as the area here if you go as far on the right hand side as on the left hand side, because the normal distribution is symmetric around its mean value, right? The shape is symmetric. We discussed it many times. It's of this form. This is the mean value. So it's symmetric around this, its mean value. So I can talk about the probability of this mean being between A and B, and I put certain value over here. Let's say I say beta. Then it gives me an interval so that I'm pretty confident that with probability beta, I will land within this interval. And being outside this interval, there is only a probability of being outside this interval is only 1 minus beta, right? So this beta is usually chosen, let's say for example, 0.9, then you will call it a 90% interval. I'm not yet calling it a confidence interval. I'll call it that in a moment. Or you can choose beta to be 95, so that interval, if you chose it to be beta to be 0.95, then you have a 95% chance that you will always land inside this interval. But how would you know this interval? If you knew the mean of the population and you knew the standard deviation of the population, then you can easily compute this interval, because then you would know that this interval is just can be computed because you know the standard deviation of this guy, which is just this. So using this normal, the normal distribution, which is totally defined by its standard deviation and its mean, you could compute this value for x bar, which I'm calling as b, and minus b, so that the total area under this curve is 0.95, and you could just compute it. But if I don't even know this mean, how would I compute it? How would I know that what is this interval? Then you don't know this interval. Rather, in our specific case where we know sigma, we know sigma, and hence the standard deviation of the mean, it is known, it is sigma over under root n. What would be the situation? The situation would be that for a particular value you get for your estimate, so suppose you land here. Now, if you land here, if you land within this interval and you compute an interval of this same size, because this size you can compute, this size of interval is governed by the width of this Gaussian, which is known. So you know the size, but you don't know where it's centered. But you know that 90, if you are putting a beta interval, then you have beta probability that you will lie within this interval. Now, if you so now you get a value and you compute the size of this using this, and so it will be something like this. So you can see that whatever value I get, I can compute this size, and I will know that with beta probability, because whenever I lie within this interval, then the mean, the true mean lies in the new interval I have created, which is centered around my specific value which I got in a particular sample. If I lie outside it, because it's symmetrically distributed, if I lie over here by chance, by that 5% chance, then if I'll compute the interval of the same size, then the mean will not be included in my interval. So I can, because of this property, I can talk about this confidence interval. So what this confidence interval is talking about, it's an interval you can give based on your estimate which you received from sample, so that you have a beta percent chance, a beta chance, beta probability that the true mean lies within this interval. Because every time you land at different values, and doing one sampling doesn't tell you that how far you are from the mean, how close you are to the mean. All you can do is make probabilistic statements. So because of what we just discussed, you can make an interval, you can give an interval. You say that I got a particular value, let's say theta. Let me say, yeah, theta. You got this value. Then based on this, you can give an interval around it, around this value, and assign to it a probability. That your true value would be within this interval. So now you see that if you increase this probability, that you want to be more sure that this is that your true mean would be within this interval, then this size of this interval will have to be increased. Because the more probabilities you increase, this size becomes bigger. And if you want to locate it with more sharpness, make the size of this interval small, you will have less probability to land in there. So you will be less sure that the value of true mean is within that interval. So the size of interval will be controlled by how much probability, with what confidence you want to say that the mean is within this interval. So that's the main idea of what a confidence interval is. So it's the probability that your estimator, you estimate whatever your estimate is, your true estimator is less than beta. So suppose you have, so we know that this x bar, which is the sample mean, which will be our observation, if I make this variable, then this is the standard normal variable. So the probability that standard normal is within a certain value, and this is standard normal with mean 0 and standard deviation 1. So the probability that it is within some range like this, where this time I want, because this mean is at 0, so I choose a symmetric range. Is equal to beta. So that means this area is beta. So this would be same as 1 minus alpha, where alpha is this rest of the area. So this probability would be same as Z and this area. If this total is alpha, then this area is alpha by 2, and this is also alpha by 2. So this is same as the probability that this ZA would be that Z is greater than ZA would be equal to, according to this figure, would be that wait. So this value, this critical value is ZA, and this is minus ZA, and you want the probability of Z between minus ZA and ZA is equal to beta is equal to 1 minus alpha. And this would be same as probability of it would be 1 minus the probability of Z being greater than Z alpha, ZA times 2, this probability, this one. So this is 1 minus alpha. So that means probability of Z being greater than ZA would be alpha over 2. Right? You want to get down to this number, ZA. This I can get from this equation, that it is that number, so that the probability of Z being more than this is this tail, alpha by 2. So this critical value, let's call it Z alpha by 2, where alpha is just equal to 1 minus beta. So what does this mean? This means if you want to put a confidence interval of 95%, then beta would be 0.95, then alpha is 1 minus 0.95, so it's 0.05. And the critical value I'm looking for is Z is greater than a particular critical value, so that the probability is 0.05 over 2, so it's 0.025. All what I need is get to this number, because this will give me the size of this interval. So like, for example, if I do it for this value, 95 confidence interval, so that will give me alpha equals to 0.05, alpha by 2 equals to 0.025, and I can just compute, again going to, I don't want to go to that table, probably it would be hard to find, going to this calculator. Cumulative probability since it measures it from here, so instead of 0.025, I have to put in 97.5. Wait. .975. So it gives me the critical value of Z as 1.96. For alpha is equal to 0.05, or for beta is equal to 0.95. Similarly, you can compute it for any other beta. Then you would know, coming back to this equation, that your confidence, you would say that the confidence interval is between x bar minus whatever this you have calculated, and x bar plus whatever you have calculated for z alpha over 2. And this part, you just give it a name. This is called margin of error. And this number is called the upper confidence level. And this number is the lower confidence level. So you got a value x bar in your sample, but you're going to compute this interval, which goes from xd to, let me just put it in brackets, from xd to x up, symmetrically around your estimate. And you say that there is a, because I did it for, that there's a beta times 100% chance that the population mean lies within this interval. So any question so far about it? So for example, let's take this example. That you have let me not go into any statements. Let me just use abstract variables. You have some variable, some population, and you don't know what their mean is. You want to estimate their mean. You are told that their standard deviation is 20. And then you pick a random sample. You pick a sample of size 64. And now you want to know from this you compute, on this sample, you compute the sample mean. And this turns out to be 75. What is the population mean?
Sir, how did you get 75?
Oh, it's just part of the statement. This is told to you. So this we know, this is given. So you had a population, you knew about the population that it has a mean, it has a standard deviation of 20. You picked a sample from it of size 64 and you computed the sample mean. And suppose you got 75. Now you have no idea what is the population mean and you want to estimate it. So what is the population mean? You can't tell, you can only estimate. And you can, what the best you can do, give an interval, give a confidence interval of for estimate of the population mean. Because these maths, the population mean and the mean of the sample means, they match, but you don't know what is the population mean and you don't know what is the mean of the sample means. You do not have like infinite number or a very large number of samples to compute their means. You have just one sample and from that you have picked up a mean, sample mean. So it may have landed here and you want to put an interval around it so that with a certain probability you can say with confidence that this interval will contain the population mean. And this, according to what we have discussed, you can know if you know the distribution of the sample means, which we know this is just given by a normal distribution with this standard deviation. So we can compute a 95% confidence interval using this distribution. And then we will be
Sir, so
95% sure that this interval will contain the true mean. So how will we do it? Just run this.
Sir,
Yeah.
sir, the confidence interval will be given by you. Like, for example,
No, you're computing it. You are yeah, that would be given to you. Like it's up to you, like with what confidence. So when you will be estimating, you pick a sample, you say that using this sample, I'm estimating the population mean. And as a result, as an answer, the best you can do is you say that I'm gonna give you an interval and I'm gonna give you a confidence level for this interval. So you will have to give a size for the interval and a confidence level for this interval that the population mean is within it. That's the best you can do. So it depends on how much confidence you want to predict it with. And the trade-off is that if you say it with more confidence, the interval size increases. If you say it with less confidence, then you can narrow down the size of the interval. So the standard error is just this, sorry, this standard deviation of this. Then this margin of error, so you have to add something to it. and you subtract something from it. That is the margin of error depending on what is the confidence you're putting in. So for 95% confidence, we computed that here we have to put in the standard values of the standard normal, where alpha in this case is 0.05. So the critical value of z, which gives you a probability of z being greater than 0.025. And with this, according to this formula, we multiplied it with the standard deviation of the sample. Standard deviation of the sample mean, which is known to us because sigma is known to us. So it's 2.5. This value we had just computed. So this is 4.9. So your interval is, this was your mean, 75, right? This is the upper confidence limit. And the
Sir,
lower
can
confidence,
you
wait.
explain
Lower
where
confidence limit,
1.9?
huh?
Sir, can you explain where 1.96 came
Yeah,
from?
just wait. So the interval becomes this. You can do this computation, whatever you get. This is 70.1 to 79.9. So there would be this interval around whatever mean you have got. And you can say that there's a 95% probability that this interval will contain the true population mean. And where did I get this? I computed this. Remember, I computed this over here. Here. So let me slightly change it, and let's say I wanna make a 90%, just for clarity, 90% confidence interval. So how would I do it? My beta is now 0.9. My alpha is then 1 minus beta, 0.1. So critical value I'm looking for is for the probability 0.05. That is probability that this standard variable is bigger than a certain value, this value I'm looking for, so that this probability is 0.05. This value somewhere here, so that this area is 0.05. Now, when I will go to my calculator, that computes this areas. So I'm going to tell it, look for this value, so that the probability is that my z less than this value, that probability is 95%, 0.95. So gives me 1.645. So this time when I'll compute the margin of error, this will go over there times 2.5. Whatever number you get here will be the margin of error, and your confidence interval would be margin of error. Now, what does this mean to have 95% probability that your mean is within, your population mean is within this interval? It just means what you always mean by probability. It means that if there's a 5% chance that this interval has still missed the population mean. So it means that if we make a lot of samples, every time you will make a sample, you will start with a different X bar. So every time the size of this confidence interval would be same, but it would be positioned differently. Because size is controlled by your probability, this value, what you put over here, this alpha, with what confidence you want to say it, times this is what is known to you, the standard deviation of the population, and the sample size. So every time you will get a different one. So out of all these intervals, 95% will contain your true mean. So 5 of them, if you had done this thousands of times, 5% of them would still have missed the mean, because everything is probabilistic. That's the best you can do. Now, to make sure, now in practice, what you do is you just get one value, and around it you make an interval where you say that mean lies with a certain probability, with a certain confidence. How can you make this size small? Well, looking at this formula, there are various ways. One is that if the population were more concentrated, if the value of this variable whose mean is being computed were not very much distributed in the population, then this would be small. Other possibility is that you pick bigger samples. If you pick bigger samples, this will become smaller, but only as a square root. So it doesn't get smaller very quickly. Or you could trade off this thing. If I say something with more confidence, I'm going to further ends. So value of this Z alpha by 2 increases. So if I trade off some confidence, the size of this confidence interval will become smaller. But if I want to have more confidence, then the size will increase. Any question?
सर स्क्रॉल अप करें 75 कहाँ से आया था?
ये 75 तो मीन दिया हुआ था ना, क्योंकि 75 दिया हुआ था, it was the mean of the sample. You picked one sample and computed its mean. वो आपके पास कोई वैल्यू थी,
ठीक है.
तो वो जो
Basically,
मीन होता है आपके पास, जो एस्टिमेट आएगा उसके अराउंड यू हैव टू मेक an interval of confidence.
So basically, all this computation is to calculate the margin of error.
Yeah, margin of error is one terminology. I think the term which more precisely captures the concept is the confidence interval. That you have a certain level of confidence that your true mean is within this interval. The true mean of the population is within this interval. So the name is very revealing. It's capturing the whole idea. You pick a sample, you get an estimate from that. Whenever you are estimating, you're picking one sample and you're just making an estimate. That estimate is not supposed to correspond to the true value in the population. But what you can do is you create an interval around this estimate with a certain confidence that the true value of the population lies within this interval. Any other question?
No, sir.
Okay,
Thank
let
you.
me stop here.